Hi, this is about the discussion of the first question. This question is from structure and bonding, unit 2 in your syllabus. But this question covers actually large part of this unit. It's about the electron pair geometry. It's about shape of molecule. It's about hybridization. It's about formation of bonds, mean overlapping of orbital and hybrid orbitals. It's about the bond angles. So because of that, this MCQ, although it's just one MCQ, it covers large part of this unit. Let's see how to answer this question. This is regarding SOCl2 molecule. SOCl2 molecule. First thing is to draw this diagram here, not the Lewis structure, but at least the type of bonds around the central atom, type of electron pairs available around the central atom. So we should find out that one. Here, how to select the central atom. Here, central atom should be sulfur. You learned that one in our theory class. Central atom should be the one least electronegative one in most cases. And central atom has the highest valence in the given species. In this particular case, chlorine has 1 valency, oxygen has 2 valency, sulfur has 4 valency. Then sulfur has high valency. And out of sulfur, oxygen, chlorine, sulfur is least electronegative one. Because of that, we select sulfur as the central atom. Thereafter, we place these atoms around this central atom. Then we decide the type of bonds between these. That's according to the valencies. Chlorine group 17. Group 17 means the valency 1. It can be 1, 3, 5, 7. All the valencies are possible. But in this particular case, chlorine is a terminal atom. Since it's terminal 1, so it should be valency 1. Here also valency 1 single bond. Oxygen, it's double bond, valency 2. But around sulfur, no need to go to this around, the central terminal atoms. We always pay attention to the central atom to decide hybridization, shape, and everything. Sulfur group number 16. Therefore, there should be 6 valence electrons around sulfur. But out of 6 valence electrons, how many electrons are involved in this case? The formation of bond. For the single bond, 1 electron from sulfur. From the single bond, 1 electron. For the double bond, 2 electrons. Then 1, 2, 3, 4. Out of 6, 4 electrons involved in the bonding. Then 6 minus 4, 2 remains. Means 1 pair is there. 1 pair is there. Right. That is the first thing we have to do. Thereafter, we can go for the electron pair geometry. I take it like this one, short form. Electron pair geometry. It's the first column in your answers. You can see that one. But how do we predict the electron pair geometry? We predict electron pair geometry according to VSCPR. VSCPR means valential electron pair repulsive units. If VSCPR, again, we discuss these things in theory classes in detail. VSCPR can be 2, 4, actually 2, 3, 4, 5, 6. We can have more than that. But in this particular case, we follow everything according to our syllabus. And again, we may have problem. What is VSCPR? VSCPR means simply sigma bonds plus lone pairs. In this particular case, we consider the central atom sulfur. Then single bond means, sigma, single bond sigma. Double bond, out of double bond here, we have 1 sigma and the other pi bond. Then how many VSCPRs around sulfur? We get 1, 2, 3 sigmas and 1 lone pair. Sigma plus lone pairs means there are 4 VSCPR. According to 4 VSCPR, we can predict the geometry. If it is 2 VSCPR, linear, 3 trigonal plane, 4 tetrahedral, 5 trigonal bipyramid, 6 octahedral. Those are the electron pair geometries we can have. So then in this particular case, since there are 4, electron pair geometry should be tetrahedral. That's the first one, tetrahedral. Electron pair geometry. Next, they ask the geometrical shape. Geometrical shape means simply the shape of the molecule. But shape of the molecule or ion can be predicted according to number of bonding pairs and number of lone pairs. You have to find it out. How many bonding pairs, and how many lone pairs are there. As you can see here, double bond. Here also we consider only the sigma bond in pairs, not the pi bond in pairs. So how many sigma bond in pairs we have? We have 3 sigma bond in pairs. How many lone pairs we have? 1 lone pair we have. 3 bond in pairs and 1 lone pair. Total 4 here. So 3 and 1. So 3 and 1. Again, in theory classes, I gave you that table. That table explains everything. I mean, if you get 1, 1, 0, what's the shape? 2, 0, what's the shape? 3, 0, what's the shape? 3 and 1, what's the shape? Everything we discussed. So in that case, maybe you remember 3 and 1, it should be trigonal pyramid. I take it like a geometrical shape. That's what you are given. Geometrical shape is trigonal pyramid. Trigonal pyramid. That's according to number of bonding pairs and lone pairs. Next, your question is to find out nature of SL bond. Nature of SL bond. Nature of SL bond. SL bond. We consider here this sigma bond, S and Cl, this one or this one, doesn't matter. Since it's a sigma bond, there is overlapping between hybrid orbital or atomic orbital, and this low overlapping should be linear overlapping. Only if you get pi bond, that is where we have the lateral overlapping. But sigma bond, it should be definitely linear overlapping. This question is actually, what are the type of orbitals of sulfur and chlorine that overlap to form this sigma bond, HCl sigma bond? Then we need the hybridization. You know, hybridization again predicted according to what? VSEPR. Maybe you learned that one in theory classes and you know that one. 2 VSEPR hybridization SP. For 2 VSEPR, 2 units, but we need only 2 orbitals, 2 hybrid orbitals. Then one from S, the other from P. So we have SP. If there are 3, what should be that? 1 from S. Always we can take only 1 orbital from S because a sub-energy level has only 1 orbital. We take 1 from this and there are 2 more because total should be 3, sp2. Likewise 4. 4 it should be sp3. But in our syllabus we don't have this. This should be dsp3, d2sp3 like that. 4 is our VSEPR part here according to our question. 4 means it should be sp3. Then sulfur is sp3 hybridized. This is sp3 hybridized. Therefore, in the formation of this HCl bond, the type of orbital of S involved in this formation of bond is actually sp3 hybrid orbital. Then what about the chlorine? Actually, since it's terminal atom, one can take its hybridized state or unhybridized state. Doesn't matter. If it is hybridized, you know, around this we have 4. Around chlorine, how many VSEPR? There are 4. Then it should be sp3. But normally, in the case of terminal atom, we take only what? Only the atomic orbital. We take unhybrid state of this terminal atom, chlorine. So because of that, here, unhybrid orbital mean that should be atomic orbital. So what's the atomic orbital of chlorine involved in this formation of chemical bond? You know, then in that case, we have to go to the valence shell of chlorine. Valence shell. In the case of valence shell, when you write the configuration of chlorine, atomic number 17, so it should be what? 1s2, 2s2, 2p6, 3s2, 3p5. That's the configuration. Then finally we have 3p5. Because of that, we can say here this bond is formed by overlapping between in sulfur sp3 hybrid orbital and in chlorine 3p atomic orbital. sp3 hybrid orbital and 3p atomic orbital. If there is answer like sp3 hybrid orbital and sp3 hybrid orbital, yes, it's correct. That's what I told you. In the case of terminal atom, it's also possible. Normally we take unhybrid state here. Okay, next question is about bond angle. It should be bond angle. Yes, it's called bond angle. I write it here. I don't have space here. Bond angle. So how can we predict the bond angle? This is the way we predict the bond angle. Again, according to the electron pair geometries, we can easily predict it. Linear 180, trigonal planar 120, tetrahedral around 109. I give the approximate value 109. In this case, we have two different 90, 120 both. In this case, we have 90 always. But the thing is this one, when you get a lone pair, non-bonding electron pair, the bond angle changes. Because if we assume all of these are bonds, then we get only bonding pair repulsion. Only bonding pair repulsion. But if you get lone pair, there will be lone pair bonding pair repulsion also. You know the strength of these two repulsive forces are different. Which one is greater? Which one is a stronger repulsion? Yes, you know, lone pair bonding pair repulsion is stronger than bonding pair repulsion. And there is another type. Lone pair is also there, but it's not present here. Lone pair is the strongest repulsive force. Since the repulsive strength here different, then definitely the bond angle may change. Since you get lone pair bonding pair repulsion and that is stronger than bonding pair, although the geometry is tetrahedral, we cannot expect 109. This should be definitely what? Yeah, once this repulsion is strong, the angle decreases. Angle decreases. You know, here I explain how to get the answer for this question only. I don't explain the theories because theory, you know, you done that one in theory classes. Ne? We have done in our class, actually, we have done all these things with so many examples in detail, right? So no need to explain that theory part again. I just explain how to get the answer only, right? So in this particular case, it should be tetrahedral, it should be 109. But since you get lone pair bonding pair repulsion, the angle is less than 109. Okay, so one can say 109 degrees, but it's less than 109. Now, these are the answers for these things. This is electron pair geometry, tetrahedral. So where you find it, it's in second answer and fourth answer. Trigonal pyramid, where you find it? Oh my God. Then in between, I mean, using these two only, we can find out the answer. It should be fourth one. Tetrahedral trigonal pyramid, and this should be sp3 and 3p, yes, less than 109. So because of that, for this particular question, the correct answer should be fourth answer. Then we will meet again in another question discussions. See you back.